Welcome to Green Chemistry, Kinetic Isotope Effects in Enzymatic Green Syntheses. Kinetic isotope effects arise when you replace an atom, for example hydrogen, with a heavier isotope like deuterium. Heavier isotopes have lower zero-point vibrational energy, so breaking a carbon-hydrogen bond is usually faster than breaking a carbon-deuterium bond. In green chemistry, we exploit this effect to enhance selectivity, reduce energy input, and minimize waste in enzyme-catalyzed syntheses. Now, the chemical picture. Consider an enzymatic proton transfer as the rate-determining step. For the hydrogen path, we denote the rate constant as K sub H, and for the deuterium path as K sub D. Typically, K sub H is greater than K sub D. The kinetic isotope effect is the ratio K sub H over K sub D. Let us quantify this. Each rate constant follows the Arrhenius form, K equals a times e to the minus Ea over RT. Therefore, the ratio K sub H over K sub D equals a sub H over a sub D times e to the power of negative E a sub H minus Ea sub D over RT. The difference in activation energies approximates the zero-point energy shift, about 1/2 H times the frequency difference between the hydrogen and deuterium stretches. For primary isotope effects, near 300 Kelvin, 6 to 8 is common. Graphically, an Arrhenius plot is extremely clear. On the vertical axis, we plot the natural log of K, and on the horizontal axis, 1 over T in per Kelvin. The vertical gap between the hydrogen line and the deuterium line at a fixed temperature equals the natural log of the kinetic isotope effect. The slopes are negative Ea over R, so the deuterium line is slightly steeper, reflecting a larger effective barrier. Next, the statistics. We measure replicate rates for hydrogen and for deuterium, compute the sample means and standard deviations, then propagate uncertainty for the ratio. The mean K sub H and K sub D, with plus minus 1 standard deviation, are shown here. If the kinetic isotope effect is the ratio of the means, then the uncertainty in the ratio is the ratio times the square root of the relative variances added in quadrature. To test significance, a paired t-test compares replicate differences, giving a t-statistic equal to the average difference divided by the standard deviation of the differences over root n. Finally, why this matters for green chemistry. Isotope effects can slow undesired side reactions by deuterating specific positions, leading to superior selectivity. Enzymes engineered for such selectivity can operate at lower temperatures with less energy input, and by mapping kinetic isotope effects, we optimize catalysis and minimize waste, improving atom economy. To summarize, chemically, kinetic isotope effects arise from different carbon-hydrogen and carbon-deuterium bond-breaking energetics at the transition state. Mathematically, Arrhenius and zero-point energy models quantify the ratio K sub H over K sub D. Statistically, replicate analysis with error propagation and hypothesis testing validates the measurement. Graphically, Arrhenius plots make differences in activation energy visible as parallel but separated lines. Thanks for watching.